Good afternoon, everybody. This is Yan Zhou from Electa. This video is made for ISBI 2012. I'm not able to go to the conference for family reasons, so I made this video for the presentation. The topic of my talk is automatic view classification for cardiac MRI. To give the application background, this topic is related to content-based image retrieval. If you type short axis view cardiac MRI in Google image search, these are some of the returned images, and you can find some sample image on short axis view cardiac images. And similarly, in clinical applications, usually we have some images at hand, and we want to find some similar image in a large-scale patients database, mainly for diagnosis purposes. So our task is automatically classify each image in such large-scale database to be a certain view, like if it's a short axis view or it's long axis view, etc. Basically, there are three standard cardiac views that are short axis view, 4-chamber view, and 2-chamber view. And also there are certain other types of views for different diagnosis purposes, but they are not included in our study. So for short axis view, only the left ventricle is visible on this type of view, as you can see on this image. And for 4-chamber view, it has 4 chambers visible on the image. And for 2-chamber view, it has 2 chambers visible on the image. In a typical large-scale patients database is like this. It not only has cardiac MRI, but also has some other types of MRI, like brain MRI or pelvic region MRIs. Major challenges include the following. The first is intra-class appearance variation. As you can see, those images are all short axis view images, but due to different scanning protocols, different hospital settings, and individual variation, they have totally different appearance. And the flipped image cases. The left two images are 4-chamber view images, and the right two are 2-chamber view images. Although they belong to the same class, they have a totally different local feature extracted from local patches, and it will confuse the classifier during the training process, so it brings a lot of difficulty for the classification. And there is a rotated images, like the heart is rotated in a random angle, so that it requires some rotation invariant features to be extracted, but it's very hard to be satisfied. And there is some previous work to solve this problem. There are mainly two categories of approaches. The first is the learning-based approaches. It attempts to bag some simple features on the local patches of the images and use boosting to train simple classifiers for the classification. And another category is model-based approaches. It not only model the appearance of each chamber of the heart, it also model the relationship of the chambers. And ultimately, the classification problem is formulated as an optimization problem. When we started to look into this problem, we first looked at what we got. And all we got are some DICOM files, which not only has images, but also has the DICOM header information associated with those images. And for the images part, it has been extensively studied over the years. But for the DICOM header part, it has really been studied to help the image analysis. And our question is that possible to get some useful information from the huge amount of DICOM header information? And we spent a lot of time to search for which DICOM field is useful for the cardiac view classification, and finally we got this one. And this one is the orientation information in DICOM header, which is the image orientation patient field. The definition is that it specifies the direction cosines of the first row and the first column with respect to the patient. And to explain that, we have to explain what is the patient coordinate. The direction of the axis is defined fully by the patient's orientation. For example, the x-axis is increasing to the left-hand side of the patient, and the y-axis is increasing to the posterior side of the patient. The z-axis is increasing toward the head of the patient. So this is the patient coordinate. And for the scanning slice, you have the x-axis and y-axis, and this DICOM field indicates these slice orientation inside the patient's coordinate system. And below is an example of this DICOM field. It has 6 numbers, and each number is in the range of 0 to 1. And the reason that we think this information is useful is that it's always relying on the patient's coordinate, and because for a human being, all the human being has similar heart oriented in the body, although there is some shape variation, size variation, but they are all in a certain range. That's why we think we may use this information to help the image analysis. And we plot the orientation distribution of 180 cardiac DICOM files, and we get this interesting graph. As you can see, those on this graph there are 5 clusters linearly separated. There are some flipped 4-chamber view, flipped 2-chamber view, and if we flipped those images back, we will get the clusters here. And if we flipped those 4-chamber views back, and we will have this plot. And if we combine those 4-chamber view and 2-chamber views together, we will have this very beautiful graph that linearly separates those 3 clusters. And finally, we got those very well separable clusters, and each cluster corresponds to one class of the cardiac view. For now, you might think that the classification problem is already fully solved because there are very well separable clusters already for each class. But orientation information is not enough for a robust classification. Here's the reason. For a scanning sequence, usually with the same orientation, you not only take the slice inside the heart, you also take the slice on different locations to make the heart fully covered. But for the same orientations, you only have this one image as 4-chamber view, but the other 3 don't have a heart at all. And another case is that with the same orientation, if the database has some other type of MRIs like brain MRI or bladder MRIs, depending on the orientation information, it will totally be classified as the 4-chamber view image, which is not desirable. That's why we are thinking to combine those 2 pieces of information together. That's how our algorithm works. So the input of the system is some visual information and DICOM header information associated with those images. The analysis includes 2 parts. The first part is a learning-based landmark detection algorithm that is used to analyze the visual information. It will produce a probability of the classification depending on how many landmarks are detected. And the second part is based on the orientation information from the DICOM header. It also produced a probability of the classification. And we combine these 2 pieces of information together in a Bayes framework for the final classification. Specifically, for the landmark detection algorithm, we first annotated 10 landmarks on each cardiac view, and for each landmark, we trained a classifier by the Violas and Jones cascade AdaBoost method. And for each cardiac view, after all the landmarks are detected, we computed a probability, which is the number of detected landmarks divided by the total defined landmarks. For the orientation classification, we used the previous 3 clusters here, and for an incoming testing case, we compute the probability of this orientation-based classification using the k-nearest neighbor method. To validate our approach in clinical settings, we did extensive experiments, and we selected 144 two-chamber view images, 197 four-chamber view, and 273 short-axis view images for training the landmark detection system. And the testing was done on 3 databases. The first one is database 1. It contains thousands of two-chamber view, four-chamber view, and short-axis images, which are all cardiac images and which can be visually identified. And all the training images are also selected from this database. And the second database that we test on has over 1,000 cases, which are either unsure images or unseen images. And none of the training images were selected from this database. And the cases in this database include some certain types, but it also includes some uncertain types, as you can see some image examples here. And the third database is the testing for stability of the approach for practical clinical use. So it has a large data set of over 10,000 unseen cases, and none of the training images are included in this database. It not only contains the usual cardiac images, but also contains some other types of MRIs like brain MRI or bladder MRIs. So here is the confusion matrix for database 1, and as you can see, after several iterations of training and testing, we reached to a very accurate stage of the landmark detection system, which has the over 99% accuracy for each kind of view. And this is the confusion matrix for the third database, which includes over 10,000 testing images. And as you can see, by diffusion of the visual and the DICOM header information, we can get very high accuracy in this very large unseen database. Here are the detection results for this database. As you can see, it not only contains the cardiac images, but also all types of MRIs, which are all correctly detected and classified. The talking slides are available at my website, and if you have any questions, please feel free to drop me an email. Thank you very much for listening.